Algebra is the wedge product. The wedge product is multiplying. If you use the wedge product to multiply an S form and an R form, you get an S plus R form. For example, the wedge product between two cotangent vectors are in lambda 1. The wedge product of two cotangent vectors is a two-form, a differentiable two-form. Then we define the exterior derivative. The exterior derivative maps differential forms into differential forms. It is an anti-derivation, which means sometimes it obeys the Leibniz rule, but sometimes with an extra minus sign. It's an anti-derivation of degree k equal 1, which means that it increases the degree of a differential form by 1. If you apply the anti-derivation d onto an R form, you get an R plus 1 form. Now that's all good and fine, and we discussed some nice uses of the exterior derivative, but it's not a directional derivative. What if on our manifold we want to directionally differentiate our differential forms? And we do know how to directionally differentiate zero forms, which is functions. Namely, the directional derivatives are given by the tangent vectors. A tangent vector applied to a function gives us the directional derivative of that function, which is itself a function. So we know how to directionally differentiate functions, or zero forms. But how can we differentiate R forms, general R forms, in a particular direction? Preferably by using a tangent vector again. The tangent vector is supposed to give us the direction in which we want to differentiate. How can we do that? How can we specify with a tangent vector a directional derivative for differential forms? The plan for that will be to proceed in two steps. The first step, step A, will be to define an anti-derivation Rxi, the so-called inner derivation. And even though it will be a derivation of the Grassmann algebra, it will not actually be a derivative in the usual sense, in the usual Newton-Leibniz sense. It will still be a derivation, though it will obey a Leibniz rule. The reason why we will introduce it is that it brings psi, a direction vector, into the game. It involves the direction vector. This is how we can get directionality into it. And then secondly, in the second step, we will combine this inner derivation, which depends on a tangent vector psi that specifies a direction. We will combine that with the exterior derivative to obtain then, in a combination of the two of them, a new derivation, which will be the directional derivative on differential forms. So here we have already a derivation. We will define another derivation. This one is has k plus 1, so it increases the degree of the differential form. This one will decrease it by 1. The combination will keep the degree the same, and that's what we want. So overall, we have one derivation, another derivation. We combine them to get a third derivation, which will be the desired directional derivative. Just like a tangent vector field is mapping functions into their directional derivative function, this new directional derivative will map differential R forms into their directional derivative, which will also be a differential R form, k equals 0. And this directional derivative defined on differential forms will be called the Lie derivative. We will first define it algebraically in this way, which is nice because we will see what the structure of it is in a coordinate system independent way. And then, just to make it more clear what the Lie derivative is, we will also do it in coordinates. And we will generalize it so that it can act not only on differential forms, but on all tensors. And then we will see what it really does behind the scenes. It has to do with diffeomorphisms and infinitesimal diffeomorphisms. Okay, so the first step, remember, we do a two-step process. We define the inner derivation, which will not really differentiate in the Newton-Leibniz sense of epsilon going to 0 and so on, but it brings in a tangent vector to specify the direction. And then secondly, we will combine it with the d. Okay, so we start with defining the inner derivation. Assume psi is a tangent vector field. Our aim is to define an antiderivation of degree k minus 1 to make up for the degree k equal plus 1 of the exterior derivative. So our aim is to define an antiderivation, that is to say a linear map that obeys the Leibniz rule, a linear map from the differential forms into the differential forms, lowering the degree of the differential form. And we will write that we will use this notation here for the inner derivation. The inner derivation, which depends on, it's a directional kind of thing, it depends on a tangent vector psi. So for every tangent vector psi, we get another inner derivation. So the inner derivation will map a differential form omega into a differential form I psi of omega. It's supposed to obey the anti-Leibniz rule. And remember, the anti-Leibniz rule says that if you apply an anti-derivation onto the wedge product of two differential forms, then you get the anti-derivation applied to the first factor, leaving the second one the same as it should be for a Leibniz rule, plus potentially a minus sign times leaving the first differential form the same, wedge the new anti-derivation acting on the second factor. And whether or not there's a minus sign depends on whether or not r is odd or even, r being the degree of the first factor in this product of two differential forms. It is easy to define a new derivation because, if you remember, once we define a derivation or anti-derivation on 0 forms and on a basis of 1 forms, then it's defined already everywhere on all differential forms. That's just by linearity and by the Leibniz rule. So let us define our new derivation, I psi, on 0 forms and on 1 form. And then that induces its action on all of the Grassmann algebra of differential forms. The definitions are as simple as you can imagine. The action of the inner derivation on functions is going to be that it maps them onto 0, which is the only thing they could possibly do, because our inner derivation is of degree k equal minus 1. It has to map 3 forms into 2 forms. It has to map 2 forms into 1 forms. It has to map 1 forms into 0 forms and 0 forms into the nirvana of mathematics. Okay, so it has to go to 0. There is no minus 1 form. So this defines how the inner derivation is acting on 0 forms. How is it supposed to act on 1 forms, on cotangent vectors? Well, we define that the inner derivation maps cotangent vectors into the cotangent vector acting on the tangent vector that went into the definition of the interior derivative, of the inner derivative. Okay, and here you see already that this inner derivation is not a derivation in the sense of Newton-Leibniz directly, because you see the omega can be written as some basis coefficients omega I times the dxi. The psi I is some basis coefficients psi I d by dxi, and they act on each other simply by omega I psi I sum over all I. Of course, if omega is the differential of a scalar function, then you can view it as a directional derivative. Okay, so that's the inner derivation. We've defined how it acts on zero forms and on one forms, and therefore, by linearity and because of the Leibniz rule, we can work out how it acts on every differential form. Here's a proposition about what exactly that entails. If gamma is a S form, then the inner derivation of gamma has to be an S-1 form. And the action is actually quite simple. If you take an S form, gamma, then it is, in particular, a covariant tensor of degree S, which means that it has S inputs for tangent vectors. Yeah, because it's in the tensor product of S cotangent spaces. So the gamma has S slots to put tangent vectors in. The Ixi of gamma doesn't. It has only S-1 slots because it is now an S-1 form. Right? Because the inner derivation is of degree -1. It lowers the degree of a differential form by 1. And the proposition says that the inner derivation acts in a very simple way. The inner derivation of a gamma, of a S form gamma, which in principle takes S tangent vectors as inputs and maps them into numbers, in the direction of psi, is given by, you see, it has S-1 inputs, because it's an S-1 form. It's given by taking gamma with its S input and choosing as the first input the vector psi, and then the remaining inputs are filling up the remaining slots. So in other words, the inner derivation acts very simply. It simply plugs the psi as the first argument into the differential form. That's what it does. Here's an example of how that comes about. I invite you to prove it in a general case. Here, let me just illustrate it with a particular case. Let's say the differential form is just the the wedge product of two cotangent vectors. So the gamma is omega wedge nu, both being cotangent vectors, or one forms. Then what's the inner derivation of our gamma? The claim was it's what you get when you plug psi into the first argument there. Well, let's see. We apply the Leibniz rule. So by the Leibniz rule, the inner derivation acting on the wedge product of two differential forms, the inner derivation acting on the wedge product of two differential forms, is given by the inner derivation acting on the first differential form, leaving the second the same, and then leaving the first the same up to a possibly minus sign, and wedge the inner derivation acting on the second factor here. In this case here, we actually do get the minus sign, because it's -1 to the power 1, the 1 arising from the fact that we are dealing with 1 forms up here. The omega is a 1 form, and that means we get a -1 here. Okay, so what is this then? Well, we know that, we've defined earlier how the inner derivation acts on 1 forms, namely by the omega acting on the psi. So this is omega psi times nu. We don't need a wedge here because this is now a number valued thing. And with functions, with scalar functions or numbers, whether or not we write a wedge doesn't make a difference. And here we have a minus times omega wedge, and then this thing, this is just the evaluation of nu on psi. That's that. Okay, so this is a 1 form, right? Because that's a 1 form times a number. That's a 1 form times a number. Now, let us apply that 1 form, Ixi of gamma. Let us apply this 1 form to a tangent vector eta. just so that we boil it down to numbers eventually. So here we have that one form. We apply it to a tangent vector eta. What do we get? Well, we carry forward that number here, but in this one form, we have to put the eta as input now, right? So we evaluate a cotangent vector on a tangent vector. So we have a nu of eta minus, and then we carry forward that number, and then we have the omega of the nu, omega of the eta, and that's that. So let's compare that with the claim of the proposition. So the inner derivation of gamma on eta, the inner derivation of omega veg nu applied to eta, spelled out is the inner derivation acting on the tensor product of omega and nu minus nu tensor omega. Remember, we did this in the previous lecture, that the veg product of two one forms is simply this. And then the claim of the proposition was that the I psi, the action of the inner derivation onto a differential form is simply plugging the psi into the differential form as the first factor, into the first slot. So we have to put the psi into the omega here and into the nu over there. And then the remaining thing, which is a one form, because once we've plugged the psi into here, this becomes a number. Once we've plugged the psi into that first factor, it becomes a number. And then the remaining one form, it gets evaluated on the eta. So what we have is that omega of psi, nu of eta, here, minus nu of psi, and then omega of eta, and you see this is the same as that. So we showed here in an example that the inner derivation is really nothing but plugging the psi into the first slot of the differential form. This inner derivation has a few nice algebraic properties that I invite you to prove. For example, it's anti-commuting. So if you see, for every psi, we get a different anti-derivation. It's direction dependent, and they anti-commute. And we also have, in particular, and that follows from the first line already, if you choose psi1 equals psi2, we have that I psi squared is 0. If you apply it twice, you get 0, which is nicely reminiscent of that property here. Also, it won't be quite as deep as that. Now, remember that if psi is a tangent vector and gamma is a cotangent vector, then we defined, remember when we defined the inner derivation, we defined it by saying how it would act on zero forms and how it would act on one forms. And in particular, we said that it would act on one forms. Gamma here is one form. We said that it would act on one forms by the one form acting on the direction vector psi. And this is, this product is also therefore called the interior product of psi and gamma. So when you evaluate a tangent vector against a cotangent vector or a cotangent vector against a tangent vector, you can also view this as the inner derivation of the tangent vector applied to the cotangent vector. So the inner derivation is called inner derivation because, in particular, it implements that interior product between tangent and cotangent vectors. This, remember, has nothing to do with a metric just yet, because a metric would map two tangent vectors into a number. This maps a tangent and a cotangent vector into a number. So now that we have defined the interior derivative, we are ready to define the Lie derivative as a combination of the exterior and the interior derivatives. And we start with the algebraic definition so that we don't have to bother with coordinate systems and charts and that sort of thing. Remember that tangent vectors, as we said, are directional derivatives of functions that map functions into functions. You take the directional derivative of a function, that's a function again. And by the way, this also means that you can apply vector fields one after another. You can take a function, apply a vector field to it, you get another function. You apply another vector field to it, you get another function, and so on. This is important because, as we will later see, this enables us to define the commutator between tangent vector fields. Right? Because you can apply one tangent vector field, you get a function, and you apply another one, you get a function. What if you do it the other way around? You get the commutator between two vector fields. Anyway, for the moment, we are interested in the fact that this is an example of a directional derivative. How can we generalize that to all of the Grassmann algebra? Well, we have that the D, the exterior D, gives us it generalizes the notion of differential. And we have as another ingredient that the interior derivative gives us the notion of evaluating a tensor with respect to one tangent vector. We have a notion of plugging a tangent vector, which is a direction vector, into a differential form. So this is the idea, well, let's plug a tangent vector into a differential form to give it direction. And this is the idea of actually differentiating. What if we put the two together? Now, I'll give you a spoiler already, but we will derive it carefully. So the spoiler is that we can combine the two, the exterior and the interior derivations, in this way to obtain a new derivation of degree 0, which will map R forms into R forms, in simply this way. You apply first the exterior derivation to your differential form, and then the interior, or the inner derivation, plus what you get when you do it the other way around. So this is the anti-commutator of those two operations. So exterior, and then the inner derivation, plus first the inner, and then the exterior. That operation is the Lie derivative, the Lie derivation, and you can prove that it is a derivation and all of that. But let us get to this result systematically. So first, in order to construct the Lie derivative, let us collect some of its desired properties. Well, we want it to be a directional derivative. That's what we are looking for. And therefore, it should be a derivation, not an anti-derivation. This minus sign would mess up the intuition for it. So we wanted to obey the regular Leibniz rule. Lie derivative on the wedge product of two differential forms should just give us this product rule without any decorative minus signs. Also, it should map R forms into R forms. The directional derivative of an R form should be an R form, just like the directional derivative of a zero form, a function, is a function again. So therefore, what we want is a derivation of the Grassmann algebra of degree k equals 0. And on functions, if f is in lambda 0, it should just be the directional derivative that we know. So when we apply the Lie derivative onto a function, namely f, then it ought to be mapped into psi applied to f. Because that we already identified as being the directional derivative for functions. So it should boil down to simply this, when we write it, if we choose to write it out in coordinates. Now remember that in order to define the Lie derivative, it suffices to define how it acts on zero forms and how it acts on a basis of one form. Then the rest is automatic. By linearity and by using the Leibniz rule, we can work out how this newly defined Lie derivative will act on all of the differential forms. We could, for example, define how the Lie derivative acts on those differentials. just a sec. We already said that the Lie derivative is supposed to act on zero forms in a particular way. Namely, the Lie derivative is supposed to map it into psi on f. Now, we simply have to define how the Lie derivative is acting on a basis of one forms, and then we are done. We've defined it completely. So in particular, we could choose to define how the Lie derivative acts on these basis vectors, d psi I, or on how it acts on a bunch of df's, where the f's are not necessarily the dxi, or are not necessarily dxi. So our problem at the moment is, how is the Lie derivative supposed to act on one form? The key idea to make that choice is that derivatives should generally commute. And we have the gradient and we have the directional derivative. And the idea now is to require that they commute. So it is natural to define that the directional derivative of a gradient field, remember, a gradient field is simply anything that looks like this. Forget about that part. Anything like this. If f is a scalar function, df is its gradient field. So it's natural to define that the directional derivative of a gradient field, the directional derivative of a df, is the same as the gradient of the directional derivative of f. You see, the second part we know how to do. We know how to calculate the gradient of a directional derivative of a function. When we are given a function, we know how to calculate the directional derivative of it. Just apply the tangent vector on it. And then we know how to do the exterior derivative too, the gradient, right? It's just a d on that. And here the idea is that if we want to know how the directional derivative is supposed to act on differential one forms, then we just say that's the same thing. So if we first take the directional derivative of a function and then apply the gradient to it, the d to it, that should be the same as if we first applied the d to it, then we have a one form, and then this as yet unknown directional derivative is acting on it. In this way, we can define what this directional derivative of one forms is going to be. So we are saying that the Lie derivative is mapping a gradient into the directional derivative of the function, and then the exterior derivative, the gradient applied to that. So here we have gradient, and then apply the directional derivative, and here we have it the other way around. First apply the directional derivative, and then do the gradient. Okay, so the idea is that the directional derivative of a gradient is by definition equal to the gradient of the directional derivative. Now the right-hand side is already defined. So we define the left-hand side through the fact that we already have defined what the right-hand side is. Yep?
So this is great motivation if we want that commutation relation. Is there other ways to define this? If we get...
Oh, yes. We will get to the Lie derivative from a completely different perspective later on as well. Yep. And in fact, we will have to do it in a different way later on when we want to generalize it to all tensors, not just the differential forms. So now that the Lie derivative is a fully defined derivation, can we relate it to the exterior and the inner derivation? Okay, see, we didn't really rely on inner derivation just yet. We've defined how it acts on zero forms. We've defined how it acts on the basis of one form. That defines it everywhere on the differential forms. What's the relationship to the exterior and inner derivation? here is the spoiler again. The Cartan equation is relating the above defined Lie derivative to the inner and the exterior derivative. Now, I leave it to you to prove that the Lie derivative defined in this way is really a derivation of degree 0. It's really a derivation of the algebra, of the Grassmann algebra of differential forms of degree 0. Once you have that, once you know that it really is a derivation of degree 0, then in order to prove that this definition agrees with what we did previously, we only have to show that they agree on 0 forms and on 1 form. Because then, by linearity and the Leibniz rule, everything is the same. So I'm assuming here that you've already, in your own time, checked that this is a derivation. Now, let's check on 0 forms. Here we have the Lie derivative acting on a function. According to the Cartan equation, what is it? Well, we have to apply this to the function plus applying that to the function. So let's say we apply this first onto the function f. So we have the inner derivation of the function f, but remember, it's being sent to the nirvana of mathematics here, right? Because f is a 0 form. The inner derivation is of degree -1. There are no -1 forms. It has no chance. It has to map it to 0. That's by definition. We constructed the inner derivation in this way. So that's a 0. We can forget about that term. And then here we have that the d acts on our f first. So here we have the gradient of f, and then we apply the inner derivation to that. And if you remember, we defined the inner derivation to act in this way, that the inner derivation acting on the df gives us the df applied to psi plugged in as into the first slot, and there is just one, that's the psi f, which is what we have. Now, if we apply the Cartan equation to the to 1 forms, for example, they could be, it could be any df's, such as the dxi, which would be a basis. Then the Lie derivative applied to a df is again giving us a term from this and a term from there. Term from here is the inner derivation applied to the df, but that is the df applied to the psi, which is psi of f. And here we have I psi after d, but d applied to d, that's d squared, is 0. So in this case, the second term goes away. And we are just left with the d psi of f, which is just a statement, now following from Cartan's equation, which is just a statement that the directional derivative of a gradient is the gradient of the directional derivative again. That's what we had earlier. So indeed, this is also what Cartan's equation is saying. And since Cartan's equation is saying the same thing for 0 forms and 1 forms as what we had earlier, that shows that it will say the same thing for all differential forms. So we have Cartan's equation. Now, for any linear maps, for any kind of linear maps, in particular those from the Grassmann algebra of differential forms into itself, we can define their commutator. It's also called the Lie bracket, also called the Poisson bracket. It's called Lie bracket if there is no other multiplication, if the commutator is the only multiplication there. But if it actually arises from some algebra multiplication of some associative algebra, as we have here with the Grassmann algebra, then it is called the Poisson bracket. Yep.
You started off the motivation by trying to find a derivation that agreed with the usual derivative on function and satisfies the line field. If there's another derivation that satisfies those two axioms, that one?
remember, it would have to deviate on 0 forms and 1 forms, right? So we defined what it does on 0 forms and 1 form. And anything that does that on 0 forms and 1 forms will be the Lie derivative. So it would already have to deviate there.
Okay. So there could be another derivation that satisfies the Leibniz rule.
Could be, yeah. For example, you could define 5 times the Lie derivative that will obey the same axiom. Right? Linearity, Leibniz rule, and so on. Yeah. Yeah, I mean, it's easy to check because you only have to check on 0 and 1 forms. Okay, so we have we define the commutator between linear maps in this way. Now every commutator is called a Lie bracket, but it's also called a Poisson bracket because the commutator requires in its definition some associative multiplication, and that makes it into a Poisson bracket. What are examples of maps that we might consider here? Well, one map is the exterior derivation, maps differential forms into differential forms. Another one is the inner derivation that maps differential forms into differential forms. And now we also have the Lie derivation that maps that algebra into itself. And we can now consider the commutation relations between them. And they are non-trivial. Well, the first one is still nice. The Lie derivative commutes with the exterior derivative. So if you take a differential form and first apply the exterior derivative and then a Lie derivative, or the other way around, that doesn't matter, they commute. However, taking 2 Lie derivatives, one after another, taking 2 directional derivatives, one after another, doesn't commute in general. And you may wonder, why is that? Isn't that a little weird? Because intuitively, we would be expecting that if we differentiate in the x direction, then in the y direction, or the other way around, and first in the y, then the x direction, should that give us the same? But the thing is that it's more complicated because those psi1 and psi2 don't have to be as simple as just d by dx2 and d by dx7. They could have position-dependent coefficient functions in front of them. And that would be picked up. In any case, you may wonder, what's going on over here? Why do we have this funny subscript here? Why don't we just have a vector field here? Shouldn't there be a vector field here? The subscript of a Lie derivative is supposed to be a direction vector, a tangent vector. What is this? Well, it turns out this is a tangent vector. Remember, we said just 5 minutes ago that if you apply a tangent vector onto a function, then you get another function, the directional derivative of that function. And so you can apply another direction vector onto that now, and you can keep going. You can apply arbitrarily many direction vectors on a function. You always get another function. In particular, you can apply the direction vector psi1 and then the direction vector psi2, and then try again in the other sequence. You get, in general, perhaps 2 different functions. And so you get a commutator, a non-trivial commutator between 2 directional derivatives in general. And it turns out that not only will that commutator be non-zero, but that commutator will be a directional derivative again. That is not trivial, because it's the difference between 2 second derivatives. The claim is that the difference between 2 second derivatives is the first derivative. We'll have to see how that comes about. Because only then this makes sense. This has got to be a tangent vector field. That's got to be a tangent vector field. That commutator must be a tangent vector field. So indeed, we're using here, on the right-hand side, that vector fields have commutators that are vector fields again. here's the actual calculation. So let's say we have two vector fields psi and eta, and we apply them on a function in one sequence and then another sequence, and we take the difference of that. So directional derivative and then a directional derivative of that function and vice versa and so on, different. Okay, what is it exactly what we're doing here? Well, we have the psi acting on f. This is coefficient functions psi I times the basis vectors d by dxj. Oh, this is a j acting on the function f. This is a function again. And remember that the psi themselves are also functions generally, right? Those coefficients will depend on where you are, on the manifold. And then we get a function here. And that function has x dependence for two reasons. First, because f had an x dependence. And secondly, because the xi's have an x dependence. So then when we apply the second directional derivative on that, and here it is, eta contracted with d by dxi, then that d by dxi acts on this and on that. Okay? And similarly here we have the eta doing its directional derivative bit on the f, and then afterwards the psi does that, but this derivative picks up on the position dependence, on the x dependence, both of eta and of f. We're going to get first and second derivatives in this business. First and second derivatives of f. You see, in this case, for example, we are going to have, because of the Leibniz rule, we're going to have that the d by dxi acts on the psi and gives us the first derivative of the psi, but we also still have only a first derivative of f. But then by the Leibniz rule, there's another term where the psi is blind to the psi, leaves it the same, and acts as a second derivative on f. And similarly here, there's a term where this d by dxi is ignoring the eta and instead producing a second derivative on f. The important observation now is that those two second derivative terms, the one occurring from here and the one occurring from there, cancel another away because there's a minus sign in between. And there's simply second derivative of f, psi I, eta j, second derivative of f, eta I, psi j. And because the partial derivatives commute with another, this is symmetric. So this is exactly the same bunch of terms as over here. And so that is zero. The terms where we have second derivatives of f cancel another away. And we are only left with the first derivative terms, with the terms where this d by dxi acts on the eta, and where this d by dxj acts on the f, and where this one acts on the psi, and where that one acts on the f. So we are left with just this expression here. Only first derivatives in f. That's important. And these are just coefficient functions, just functions. So all of this stuff here, you see we're summing over I here, summing over I. So this is all just dependent on j. All this stuff we can collect into a bunch of coefficients, nu j. And so what we see here is that the commutator of two vector fields acting on a function gives us the sum over some coefficient functions, here they are, times partial derivatives acting on the function. And this is of the form of a vector field. It's just a weighted sum of partial derivatives. So what we've seen here is that the commutator of two first derivatives involves second derivatives, of course, but they cancel away. And we're just left with a bunch of first derivatives again, which is a vector field, which is to say that the commutator of two vector fields applied to a function is a vector field again, a vector field that we will call nu. Okay, so and that's why expressions such as this one up there do make sense. I subscript commutator of psi1, psi2. It's I subscript nu, really. And I leave it to you to actually prove these things. If you want to get some exercise on those derivations, this is the ideal thing to do. Any questions so far? because this is the Lie derivation, the Lie derivative, on differential forms. If there are no further questions, then let's move on and see how we can generalize the Lie derivative to tensors in general, the general tensor fields. Okay, so we know the Lie derivative is the directional derivative on the Grassmann algebra of differential forms. Can we extend it to become a directional derivative on all tensor fields? Well, not with the methods that we just had, because, for example, the exterior derivative really only acts on the Grassmann algebra of differential forms. We don't know how the exterior derivative should act on an arbitrary tensor. And we also don't know how an inner derivation should work. These things were really tailored to differential forms. So we certainly can't use Cartan's formula for that. But maybe we can identify a definition, we can find a definition for the Lie derivative that agrees with what we've just done, but is basically a Newton-Leibniz limit of a directional derivative that can be applied to both differential forms and more general tensors. So something like this. So if f is a function, then that's the Newton-Leibniz definition of the derivative. But what if f is an arbitrary tensor on a manifold? Is there something like that? At first, it would seem that there is a problem, a fundamental problem. And the fundamental problem is this. If this is a function at a point x, and that is a function at the point x plus epsilon, then this takes some value in the real numbers, let's say, and that takes some value in the real numbers, and we know what the derivative is between two real numbers. We know what the difference is between two real numbers. But if this is a tensor at a point x of the manifold, then this is an element of the tensor space at that point. Whereas if this is another point of the manifold, then the tensor that we get at that other point lives in another tensor space. We can't just subtract a tensor in a tensor space of one point of the manifold from a tensor in a tensor space of another point of the manifold. We'll have to come up with some methods to deal with this so that those two things become comparable, so that we can subtract them from each other and then take the limit of epsilon going to 0 when we divide by epsilon. So that's a general idea. Here's a geometric definition then of the Lie derivative. Remember the geometric definition of directional derivative, the geometric definition of a tangent vector. If gamma is a path in the manifold, so gamma is mapping real numbers like a time variable inside some interval into the manifold. So t is a time variable, let's say, along that path, and it maps that into points on the manifold. So t is the time on your trip, and gamma is your position on the manifold. This is a path. We assume it, of course, to be smooth. And then we say that a tangent vector, every such path defines a tangent vector at a point. So we choose a point t0 that will give us a point in time t0 that will give us a position on the manifold gamma of t0. And our path then defines a tangent vector at that point gamma of t0. And remember that was an equivalence class of paths. We put a bar over it. And that's an element of the tangent vector of the tangent space at the point gamma of t0 of the manifold. And what does this tangent vector do? A tangent vector defined through a path is mapping functions, such as temperature functions on the manifold, into the application of the tangent vector on the function, which is defined to be the rate of change of the temperature, let's say, along the path at the point in question. So we take the path, plug it into the function, which could be like the temperature function on the manifold, and then differentiate the temperature with respect to the path variable, to the time, and evaluate at the point in question. That was the geometric definition of what a tangent vector is. So that was clearly a directional derivative. Now, imagine we are given a vector field psi and imagine we are given a path gamma. So now we are not using a path to define a vector field. No, let's say we're given a vector field. So at every point of the manifold we have a tangent vector. And imagine that we have a path gamma in that manifold. Now imagine that we have chosen our path in a very particular way. Or we've chosen our vector field in a particular way. In any case, we've chosen them in such a way that the tangent vector at the point denoted by t is actually the vector field at that point. So you have a vector field in space, you have a path, and the tangent vector to the path at every point of the path is actually agreeing with what the vector field does at that point. It's the same vector as the vector field's vector there. In this case, we say that the path is a so-called integral curve of that vector field. So for a given vector field, a path is an integral curve if its tangent vectors agree with the vector field wherever the path travels. It turns out that locally we can always find such a pair. If assuming the vector field is smooth enough, we can always locally, that comes from the theory of ordinary differential equations, there always exists such a path that is an integral curve. Maybe it doesn't go very far, but there always is one. And that means that every vector field defines a flow. So you can always view, at least for a very short time, you can always view a vector field as defined as being a velocity field of something that's moving. A flow. Now let's say we follow these paths for a small amount of time. Generally, we can't follow them for a long amount of time. Let's just say for a small amount of time. Actually, we only need infinitesimal eventually. What does it mean? So here we have the manifold, and we have a vector field in it. And here are integral curves for that vector field. I just drew a bunch of them. Now, if you take those integral curves and you start with the particular time t0, then you are at a particular bunch of points. For example, at t0, you might be on this point for this path, on that point for that path, on that point for that path. And then you run the evolution forward, you follow that path, you follow that integral curve for a fixed amount of time t, and then you end up a little bit later, downstream, so to speak. You end up a little bit downstream that integral curve. And you see, if you started here, you would be a little bit later over there. So after a certain amount of time t, any point of the manifold has flown a little bit further, some other place. What this means is that the integral curves of a vector field will generate a map of the manifold into itself. See? Because at every point of the manifold will have an integral curve associated to it. And if you follow that integral curve for a certain fixed amount of time, t, then you'll end up somewhere else. And that's true for every point of the manifold. So every point of the manifold flows somewhere else. And what that means is that every point of the manifold gets mapped into another point of the manifold. That's an automorphism of the manifold. Or it's a diffeomorphism of the manifold into the manifold. Because we do this in a differentiable way, of course. So what we have is that we have here the manifold and the flow by a certain amount of time, which we will keep small, but for the moment finite. The flow will map the points of the manifold into the points of the manifold. At least locally, you can always do this for a certain finite amount of time. Now remember those pictures that we had earlier of diffeomorphisms from manifolds into manifolds. They induced pullbacks and push-forwards. Was that your question?
No.
Okay.
So in this diffeomorphism, we can result in like regions not being covered, right?
No, remember that there's a theorem from the theory of ordinary differential equations that for a smooth vector field, you can always locally find a flow.
Yeah, you can locally find a flow.
Yeah.
But the resulting flow could miss areas, right? Or does it have to be constant?
Yeah, well, that's right. Yes, I think you're right. You may not hit every point of the manifold in this way. You could have like an overall shrinkage. That's right.
So yeah, to have a nice and continuous vector field to have your flow on, you need at least you gotta agree on a simple chart. You gotta have.
You need a chart to actually write it down, but
Yeah.
to actually define it in principle, you don't need. It's not relative to a chart. It's just a map of points into points, but of course in practice, how
Yeah.
else would you write it down than in coordinates?
But here you're saying at least locally, you know, what is.
By that I mean a patch, a finite size patch.
So, for example, if you took like the top half of the sphere and all the vector field just had it smoothly come to
That's
the
right.
North Pole. At the North Pole, you'd have a problem since all of the things.
Yeah, you run into problems like that. Yeah. Okay, so we have a flow of diffeomorphism. We have a flow defined by diffeomorphism. So in particular, if you look at a finite amount of time, then it's just one map from the manifold into the manifold. And I didn't put here again the pictures for the pullbacks and the push forwards, right? Remember that if you have a diffeomorphism from manifold to manifold, then it means that the function germs get mapped by an algebra homomorphism in the other direction. And then there is the tangent map, which maps tangent vectors here into tangent vectors there. And that would be a push forward, because it's twice, right? I mean, it's a pullback for the function germs, but it's a push forward for the tangent vectors. And then the cotangent vectors go the other way again, because they are evaluations on the tangent vectors, right? And so it goes back and forth. And for general tensors, you have a mix of both going on. But the point is that there is, if this is an invertible differential, if this is a diffeomorphism, then you have isomorphisms down here as well. Algebra isomorphisms and isomorphisms between the tangent spaces and the cotangent spaces and the tensor spaces. This will be crucial because if you remember the problem that we had earlier, we wanted to define a Newton-Leibniz kind of derivative. And we said, how can we take the difference between a tensor here and a tensor there? Well, you see, if we have a map of tensors here to tensors there, then we can take the tensor here, map it through a pullback or push forward to a tensor at that point, and then they live in the same tensor space. We can take the difference, divide by epsilon, take the limit. This is basically, I already gave it away. That's all of it. But we have to write it out explicitly, and here's how it comes out. Okay, so diffeomorphisms on manifolds induce corresponding isomorphisms of the tangent, cotangent, and all tensor spaces at the point P. And so in particular, our diffeomorphism phi, the flow for a finite amount of time t, is going to induce a phi star, which maps the tangent space, the tensor space, the space of RS tensors into the space of RS tensors in the remote location, in the location where you float to. And that thing we assume to be invertible because we assume our diffeomorphism to be invertible. So what we have is that every tensor field tau, so tau is now a tensor field, right? So it assigns to every point of the manifold a tensor. And let's say it's an RS tensor, R-fold contravariant, S-fold covariant. Then we already have now a notion of a tensor field not changing under the flow. This would be very important. For example, when the tensor field in question will be the metric, then we will get killing vector fields in this way. But I'm getting ahead of myself here. So let's say tau is some general RS tensor field. Then we say that tau is invariant under the flow induced by some vector field psi if, when we evaluate the tensor field at the remote location, at the location where you float to after the flow took place, if that's the same as evaluating the tensor field at the point where we started, and then mapping with the induced isomorphism into the tensor space at the remote location. Okay? If that's the same, then we say that our tensor field is invariant under that flow, under that induced map. And that would be occasion to say that, I mean, if this is true for arbitrarily small t, then we would say that the derivative, the directional derivative in the direction of that flow is 0. But we want also non-zero derivatives. So we will use this definition then, and that's the Newton-Leibniz definition of the Lie derivative. You will say that the Lie derivative, according to its geometric, as opposed to the previous algebraic definition, of any arbitrary tensor field tau at a point P of the manifold, which happens to be, by construction, the time equals 0 point of a path that runs through the point P. So we have a vector field, and gamma is one of its integral curves. And the integral curve for its argument value equals 0, at time equals 0, so to speak, will be at the point P. Then the Lie derivative of an arbitrary tensor field tau at that point, with respect to the flow induced by the vector field psi, of which gamma is an integral curve, is defined in this way. And this hopefully looks already a little familiar now. It clearly has the form of a Newton-Leibniz limit, in that it is something minus something divided by t, t going to 0. Here is the tensor field at the original point. And then here we have the tensor field evaluated at the point where you flow to and mapped through this induced map of the tensor spaces back to the point where you started. So they both live in the same tensor space, namely the tensor space attached to the point P. Take the difference of them, divide by the amount of time t that you let things flow along the integral curve, and then take the limit for t going to 0, and that's the Lie derivative. And amazingly, that turns out to be the same for differential forms as what we defined algebraically previously. But it shouldn't be a surprise because that thing is going to obey a Leibniz rule. And we know that, you know, if it obeys the Leibniz rule and a few other conditions, I mean, if it obeys the Leibniz rule, acts the right way on 0 forms and on the basis of 1 forms, then you've already fixed it. Okay, so this is the same equation, just with a little bit more detail. So this is the vector field, the tensor field, evaluated at the point P in question. Right? You want to know what is the Lie derivative in the direction of psi of the tensor field at the point P. So we take the tensor field at the point P. Then we take the tensor field at the point gamma of t. Gamma of t is not gamma of 0. Gamma of 0 is the point P. Gamma of t is the point where we've flown to after amount of time t. So we evaluate the tensor field at this remote location, and then we take the inverse of that isomorphism that maps tensor spaces into tensor spaces to map that tensor now into the tensor space that's attached to the point P itself. So this is an element of the tensor space at the point P of the manifold, as is this one. As is this one. So we can take the difference between the two, 1 over t and the limit, and that's going to be the derivative. Now, how does that explicitly look like in a chart? This is important but tedious. This is the point where we have to drop the summation symbols. And probably this was also the point where Einstein dropped it and came up with the summation convention, that when two indices, when an index occurs twice, you're supposed to sum over it. Okay, so let's work this out in a chart. This thing. What is that exactly in a chart? Well, phi is our diffeomorphism that maps the point x into the point x tilde through some flow, which we will eventually make infinitesimal by letting t go to 0. So we expand the x tilde, the new coordinates x tilde, we expand the new point x tilde in terms of the old point plus t times psi. We only need the linear approximation because we take the limit for t going to 0. So remember, we are not changing coordinate system here. We are mapping points into points. So the x tildes are the points where you flow to. That's the remote location, the x tildes. And where you flow to depends, of course, on where you started. So you have x tildes of x. And at time t equals 0, x tilde of 0 is just x. And then you flow further in the direction of the direction vector. That's why you have that expansion in the first line. Okay, so we have that the new location, the remote location, is expressed in terms of the old location plus t, plus a term linear in t. Now we're dealing with tensors, and tensors have particular transformation properties of their coefficients when we use the standard bases of d by dxi and dxi, the usual differentials. We established exactly how they transform. Did I put it earlier here? No, not really. Okay, but we'll get to that in a moment. Let us look at the Jacobian matrix. We will need it later for writing down how the coefficient matrices of these tensors change as we apply the diffeomorphism. And how do they change? Well, that's just calculated from the top line here. We just differentiate with respect to the x. And then we get that term plus this term plus higher order terms. From now onwards, we will start to write those derivatives more consistently as just a comma. Right? So instead of d psi by dxj, we just write psi comma j. What is the inverse Jacobian matrix? It's just that thing with a minus sign. I invite you to prove that this is true. It's of course only true to linear order in t, right? But check it out. Just multiply this with that, integrate, sum over the indices, keep only the 0 and first order in t, and you will find that this is right. This is the inverse Jacobian. We will need both of them because we have covariant and contravariant indices. Well, and so now we need the image of the tensor at the remote point. So what is the tensor field evaluated? What is the tensor field evaluated at the later point x tilde? Okay, so the tensor at the later point at x tilde is given by this expression here. It's the tensor at the point x tilde, the tensor field at the point x tilde, with the coefficients transforming in this way. The usual way, because we have covariant and contravariant indices here. So remember what we're doing here. We are taking the tensor field at the remote location, at x tilde, and we want to know how that tensor field looks like at the original point under the induced isomorphism of the tensor spaces. That's the phi star inverse. That's the inverse of the induced isomorphism between those tensor spaces. Remember, that's the thing that we need for the Newton-Leibniz expression. The tensor field at the remote location, tau of x tilde, but using the isomorphism mapped into the tensor space of the original point where we want to evaluate the derivative. Okay, so here we have the tensor field, and then under this induced map of the diffeomorphisms, I mean, we worked it out already how that works, we get the tensor field, and then we have these transformation matrices for the covariant and contravariant indices. Now let's expand that. Let's Taylor expand that. Well, the tensor field at the remote location is given by the tensor field, the remote location expanded, which is the original position plus tau times psi. Remember, that is the flow of the points that we had a little earlier. Here, the top line of this page, right? The psi tilde is x plus t psi I. Flows in that direction. Okay, so we have this. And then those Jacobian matrices, we just worked out what they are to lowest order. These guys. Okay, so that Jacobian matrix is the Kronecker delta plus that. This Jacobian matrix is the Kronecker delta minus that. If we plug all that in there, we obtain the expansion for the tensor field, for the tensor field's coefficients, and then these expansions for the Jacobian matrix. And we only keep the first order. We only keep terms up to linear terms in T. So for example, a term with a T psi here and a T psi there, they would be T squared, and so we can forget about them. Let's see, before we can simplify things, let us first spell out what that is, that thing. It's, these are coefficient functions, and we have to evaluate them not at x, but at x plus t psi. Let's Taylor expand that. So what that is the coefficient functions at x plus the linear term, which is t times, and then that differentiated with respect to d by dxk, and then summed over the psi k, because that's this thing here when you spell it out explicitly. Okay, that's just the usual Taylor expansion of a function. In this case, it's lots of them, lots of coefficient functions. And the psi, remember, is not being differentiated here. It is just a bunch of coefficients that give us the direction in which this Taylor expansion goes. This is just literally the directional derivative of those functions, of those coefficient functions. And then we have all those terms here where you notice the psi are differentiated. See that there? Derivatives in the psi in there. So the rest is carried forward here, except that we dropped the terms that would be proportional to t squared. Let me remind you of what we are calculating. We are calculating what you get when you take the tensor field tau, evaluate it at the remote point x tilde, and then put it back to the tensor space where we started. And what we get is the original tensor, this thing, plus a bunch of terms to first order. And they are of the form of a derivative of the tau itself, contracted with the psi, not differentiated, and then terms with minus or plus signs, depending on whether they are dealing with contravariant or covariant indices. And those terms have derivatives of the psi vector in them. So in this case, it's the psi that are being differentiated. So now that we have this expression here, we can evaluate the Lie derivative according to our geometric definition, because we evaluated what this is. It's this whole bunch of stuff up there. So the Lie derivative is this, which is all of that, minus this, divided by t, limit t going to 0. Now that is just the first term up there. So what we are left with is just this bunch of terms, where the t has now dropped out. Okay, so we see that the Lie derivative of a tensor given by a coefficient matrix in the usual basis is given by first ordinarily differentiating the coefficient functions of the tensor in the direction of the direction vector. And that's what you would expect for a scalar function, just the directional derivative as usual. But then we also get a bunch of terms which contract the tensor with derivatives of the direction vector psi. So in particular, for any contravariant index, you have that this index contracts with that derivative here, and that goes on for I1 all the way to IR. And for all covariant indices, you have similarly terms from J1 to Js. Each time you're differentiating your direction vector. If you choose your vector field to be a vector field whose coefficient functions are not position dependent, then these terms would all drop out. We're not so lucky usually, right? But then all those terms would drop out, and we would have just this simple directional derivative. But in general, when the direction vector field itself is position dependent, then we acquire all those extra terms there. And of course, ultimately, this is meant to be an abstract thing, not dependent on any coordinate system. So it's the generic case, the abstract case, that we carry along all those other terms as well. Now, is this definition, tedious as it looks, is that equivalent to the algebraic definition of the Lie derivative that we had earlier? Well, if we can show that what we have here is a derivation, and if we can show that it acts the same way on 0 forms and 1 forms, then we know that it does agree. So let's first check that it does the same thing on 0 forms and 1 forms. Let's say our tensor in question is just a function. It's a 0 form. So then tau is simply tau of x. It has no indices. And therefore, the Lie derivative on our tensor field, which is just a 0 form, just a function, is by the above formula simply this, right? Because there simply are no no indices, no contravariant or covariant indices to contract with derivatives of the psi field. So we're just left with tau, comma, k, psi k. So we obtain that. And therefore, the Lie derivative is just the ordinary directional derivative on scalar functions. What if we apply our Newton-Leibniz defined Lie derivative on a covector field, which is to say on a one form? So if tau is a one form, then it can always be written, at least within the validity of a chart, it can be written as some coefficient functions, tau j, times these basis vectors of the cotangent space. And then let's see how the Lie derivative acts on that. I just give you the start of this. The Lie derivative acting on a one form will have two terms according to this lengthy formula up here. Remember, there will be one term where you differentiate the tensor itself and contract that with a direction vector. And then dependent on the index structure, you get potentially several more terms where the direction vector is differentiated. And in this case, we get one more term, right? We get first the term where the tensor itself gets differentiated. So it's tau j, comma k, and the direction vector does not get differentiated. Plus one more term, because we have one index here in this tau. We have this tau j index. So we have this index, and then we have a derivative of the direction vector, and it's all contracted in such a way that it makes sense. And I leave it up to you to check that this is also the same thing as what you would get with our previous algebraic definition when you apply the Lie derivatives algebraically defined on cotangent vectors. It's really just one or two lines. Finally, let us collect quickly some properties of the Lie derivative without proof. Again, you're invited to check. The Lie derivative is indeed, and in this case now, this is the Lie derivative on all tensor fields. The Lie derivative maps RS tensors into RS tensors. In particular, the Lie derivative of a vector field turns out to be the commutator. So the Lie derivative in the direction of a vector field psi applied to a vector field eta is actually the commutator of these vector fields. Remember, we showed that this is a vector field too, because the second derivatives cancel each other away. We also find linearity in the argument. If you do the directional derivative in the direction of psi plus eta, you get the same as directionally differentiating a tensor with respect to psi plus doing it with respect to eta. That is very nice to know. And the Lie derivative in the direction of the commutator of two vector fields is actually the commutator of the Lie derivatives. In fact, the Lie derivatives, you can use them to define a Lie algebra. So does this still obey a Leibniz rule? And that's the last thing I want to mention today. Yes. It turns out that the tensors, general tensors, not just the differential forms, but general tensors also have a multiplication, of course, and that's the tensor product. You can take two arbitrary tensors, antisymmetric or not, covariant or not, and then just multiply them with a tensor product. And it turns out that you get an algebra structure also in this way. And the Lie derivative defined on all tensor fields is actually a derivation on that algebra. We're not going to use that algebra very much, but it's nice to know that we could have defined this Lie derivative on general tensors also from an algebraic perspective. But it seemed useful to do it geometrically with the Newton-Leibniz limit, because what we see now is that what the meaning of the Lie derivative is that it gives us the change of a tensor field under the flow, under an infinitesimal diffeomorphism induced by a direction vector field, where the key map needed to form the difference in the Newton-Leibniz limit is obtained by these pullbacks and push forwards. Okay, so that much for today. On Friday, we'll start reinventing integration. Okay, any questions?
I can't remember exactly. Is the flow a Lie group or not?
The flow a Lie group.
Well, it looks like it satisfies properties.
Let me make it more precise. The flow, the infinitesimal flows are generated by the Lie derivatives, right? They give us the infinitesimal. And what we see is that the commutator of two flows is a flow, and so you get a Lie algebra of them. Now, how do you go from a Lie algebra to a Lie group? You can't always, that's right. It's like the exponentiation.
Yeah.
And
It has to be like subjective and injective.
their conditions. Yeah. But the basic necessity for a Lie algebra is that the Jacobi identity holds, in order to have a chance of being able to exponentiate to get the Lie group.
Do you have a suggestion in a small local space? Because usually in a Lie group you have a suggestion in a small space, and then you generate the group by that way.
I'm not exactly sure what you mean. But remember, maybe the answer to your question is that we know that there's always some finite flow, right? Okay. Remember that Friday again we'll be in this room, but then next week we'll be back to the Alice room.